Nowadays, when you say, I study gravity, it can mean 3,000 things.
Yeah. And I was very disappointed in kind of day one of my PhD when they gave me some reading. It's not just neutrons. It's like, oh, that's the name, but it's a lie.
If I want to know something about a very hard to control animal like a puma, then I can use my cat to understand something about the puma.
We hope you liked getting to know our researchers in the last video. This video, you're getting to know them even better by learning more about their research.
The shortest way how to describe myself as a researcher is that I'm someone that studies classical and quantum aspects of gravity in the framework of string theory.
I am interested in neutron stars, basically, so kind of collapsed remnants of massive stars that where you've got maybe 1 to 3 solar masses of material in a kind of tiny sphere 20-30 kilometers across.
I'm broadly interested in quantum simulation and quantum computing, and in particular I like to work very closely with experiments, so that's why I also share my office with an experimentalist.
Nowadays, we're entering, from my perspective, a very interesting and exciting time of gravitational physics. Where there's a lot of opportunities, there's been a lot of breakthroughs from a theoretical point of view, from an astrophysical point of view, from mathematical perspectives. There's been a lot of advancements. This creates a lot of opportunities, but we also have a lot of challenges to go ahead. And so nowadays when you say, I study gravity, it can mean 3,000 things.
Yeah.
Because you have to put it into context. What does it mean for you to study gravity? And it's an area of theoretical physics that doesn't mean that, I only do general relativity, or I only do whatever people think string theory is. It basically means that you're, in a lot of contexts, it means that you're a theoretical physicist that has to understand many, many different subjects of theoretical physics. So I, for instance, I like to study black holes, but in order for me to understand black holes and to understand classical aspects of black holes or quantum aspects of black holes, you need to be an expert, besides general relativity, you need to manage a lot of concepts in quantum field theory, try to understand non-perturbative aspects of quantum field theory. This ranges from understanding concepts like supersymmetry, conformal field theory, having a good understanding of statistical physics. Mathematics becomes extremely useful. It can be things like differential geometry, but also tools that I use are related to also like number theory as another example, another area. And then it starts growing and growing.
I am interested in what is happening both on the surface and in the interior of the star. So one of the big questions about neutron stars is, what exactly are they made of? And I was very disappointed in kind of day one of my PhD when they gave me some reading. And it's not just neutrons. It's like, oh, that's the name, but it's a lie. They might be mostly neutrons, but they're really like kind of, small planet-sized atomic nuclei. Very, very neutron-rich if they are composed primarily of neutrons. But there could be all kinds of interesting states of matter in there, stable states of strange matter, either locked up in particles like hyperons or in the form of deconfined quarks, where you have up, down and strange quarks out of individual particles forming this kind of nuclear goo in the core of the star. We have kind of, crystalline solid crust of the star as well. So you have kind of ultra-dense nuclear fluid in the inside of some kind. You've got a solid crust of kind of white dwarf material on the outer part. So really interesting from a nuclear physics perspective. There are also all kinds of interesting surface phenomena on neutron stars. They spin super fast, they have really strong magnetic fields and magnetic flares. Some of them accrete material from a companion star, and they have that whole accreted kind of ocean blows up every now and again with thermonuclear explosions coming from this. So loads of fun astrophysics and quite a lot of fun physics to do in here as well. The last few years, I've really been involved with the idea that we might be able to probe both the subsurface of the star and what's happening on the surface by making kind of X-ray maps of the surface. And there are a couple of X-ray telescopes that have really started to let us get to grips with this. A lot of the groundwork was laid with RXTE, which is the Rossi X-ray Timing Explorer. It's the first X-ray telescope I worked with in my first postdoc at NASA. Operational 1995 through to 2012. So I was working on it when I first moved to Amsterdam. But really great X-ray telescope that was very good at timing photons. And then there's this new telescope, NICER, which is the little box in the middle of the screen here. NICER is on the International Space Station. Again, it's an X-ray telescope. It's the Neutron Star Interior Composition Explorer, basically, but mounted on the space station. And both of these telescopes essentially allow us to map what's happening in neutron stars. We are uncertain of what exactly sits in the core of neutron stars. So we don't know if it's just neutrons or weird particles or whatever. We also don't know how those particles interact. I mean, if you have a system with 95% neutrons, you cannot test how squashy that is on Earth because you can't make that state of matter. So we have uncertainty about what's in the middle of the star. So we don't really know the forces between the particles or what particles are there. But basically, if you scale that up to the whole star, what we say is we don't understand the equation of state. And the equation of state is basically the pressure-density relationship within the star. However, the equation of state is one of the ingredients if you want to build a stellar model. So basically, if you are trying to build a star as a theorist, you set up the force balance equations, you're balancing gravity and pressure gradients, you pop in an equation of state, basically, which could be something like a perfect gas equation, and you basically then crank the handle on the equations, and what you end up predicting is a mass-radius relationship. So now we're getting a step closer to something we can measure because the mass and the radius of the star set its gravitational field, along with the spin. And because they're really dense objects, they have a relativistic space-time. As the star spins, you see the overall brightness going up and down, and you see the spectrum, the energy function of the radiation changing as well. So there's just a little cartoon on this movie here. If you have a hotspot, if you have just boring Newtonian gravity, hotspot goes around the back of the star, you don't see it, emission vanishes. Relativity does funny things like light bending. Now I can see the back of the star still because the radiation is being bent because of the strong gravity. So now the spot never vanishes. And that's just one of the relativistic effects that we use to kind of model the emission that we see from these stars. So what we can in principle do is look for radiation coming from the surface has to get to us through this strong gravity environment, and it's going to pick up signatures of mass and radius on the way. If we can get the mass and radius, we can then walk the whole way back around this loop effectively and then get to the nuclear physics. At least that's the idea of what we're trying to do.
One of the topics we work on is trapped ion quantum computing, and in principle what we really want to do is to have really close theory experiment collaboration to have verified quantum simulators, because we want to know that what we build actually does what we want it to do. And also we want to be able to use our systems to understand a variety of different things, and I'll tell you a little bit more about it. But in principle, the idea is that quantum mechanics and the ability to use it will give you advantage in different areas. And it can be in making better sensors, but it can also give you better algorithms. But also a lot of the systems that you have to use are not ideal systems, and they can have dissipation in them, and you need to be able to also control those aspects. So these are sort of the different lines of the research, and they are all very connected to each other because they, in the end, will allow us to have this quantum advantage. One of the ideas is that we want to really use a quantum computer, and the way we think about a quantum computer, and maybe in sort of public domain, like sort of publicity-wise, you always think about Shor's algorithm and you think, oh, this is great, it gives you an advantage. But what we want to do instead is we want to be able to simulate physics with our quantum computer. And the way you can think about it is that we want to use a very easily controllable system. This is my cat, she's very nice. And if I want to know something about a very hard to control animal like a puma, then I can use my cat to understand something about the puma. And that's sort of the idea now. So now we use our favorite systems that we can build in the lab, and they're perfect and they're controllable, to understand things about many quantum particles interacting with each other, both sort of when they're out of equilibrium or when they're in equilibrium, and understand their properties. And these systems can be less ideal than what we build in the lab, but the lab will give us a way to test our theories, basically. Maybe I'll tell you a little bit about how these trapped ions will work. They're one of the best platforms we have for quantum computing and simulation. They have very long lifetimes, and they allow us to make systems that every ion interacts with every other ion. What we wanted to do was to make a more tunable system, and also maybe make simpler infrastructure for a quantum computer. And you can see if you have a crystal of trapped ions, they move like any normal crystal. So you can see that here the ions can move in different ways, in plane or out of plane. And you can use the motion of your crystal to actually create effective interaction between your ions. And maybe the way now you want to change the interaction then is to change the motion of the ions. So if you change the motion, you can change the type of interaction these things have. And then it ends up that you can do many different types of models. Of course, you can't do any model you want, but you can do many different cats. So you can imagine you can do many different models of a same family.